The night sky, in its serene and silent majesty, is a deceptive canvas. It presents an image of calm, of order, of a timeless, unchanging peace. But this is an illusion, a beautiful and comforting lie we tell ourselves in the quiet of the night. The universe, in truth, is a vast, chaotic, and often terrifying abyss. A place far more ruthless and unpredictable than we dare to imagine. It is a cosmos filled with objects of unimaginable power, objects that would rip us apart, atom by atom, if we were to stray too close. And yet, we cannot stay home forever. There is a deep and insatiable curiosity woven into the very fabric of our being. An innate human drive to leave the familiar shores of our own world and to venture out into the unknown, to explore the vast, dark ocean of the cosmos. At first, this journey seemed harmless, a gentle exploration of our own cosmic neighborhood. We started with our neighboring planets, with Mars and Venus, with the familiar, cratered face of our own moon. We stepped onto its surface, thinking of these celestial bodies as cold, barren, and ultimately benign landscapes. But as our gaze sharpened, as our instruments became more sensitive, we began to understand their true nature. We discovered Venus, a hellscape with a crushing atmosphere of sulfuric acid and surface temperatures hot enough to melt lead. We found Mars, a world of planet-engulfing dust storms and a thin, unbreathable atmosphere. These worlds were anything but friendly. They were stark and powerful reminders of the razor-thin margin of safety that our own world provides, and still, we pushed further. In the 20th century, our reach extended beyond our planetary neighbors. We discovered the asteroids, the comets, the rocky debris left over from the formation of our solar system. And we learned that a single chance collision with one of these celestial wanderers could end life on Earth as we know it, just as it did for the dinosaurs millions of years ago. We came to understand that the serene night sky is not a peaceful sanctuary, but a cosmic shooting gallery, and that we are living on a fragile, blue target. But still, we did not stop. Our curiosity, our unquenchable thirst for knowledge propelled us ever outward, further and further into the cosmos, into the darkest and most enigmatic of its secrets. And then, we found the black holes. We discovered regions of space-time so warped, so dense, that nothing, not even the fleet-footed particles of light, can escape their gravitational grasp. We found the ultimate cosmic prisons, the final, one-way destinations of the universe. And yet, even in the face of this ultimate terror, we did not stop. We are a species defined by our courage to look into the abyss, to confront the unknown, and to ask the deepest and most profound questions about the nature of the reality we inhabit. Our journey into the heart of this strange and often terrifying universe begins at the smallest possible scales, with the fundamental building blocks of everything we know. At this subatomic level, all the matter and energy in the cosmos is made up of particles tiny, indivisible entities that come together to form the atoms, the molecules, the stars, and the galaxies that populate our world. But these particles are not what our classical intuition would lead us to expect. They are not like tiny, solid marbles or microscopic billiard balls. They do not have a well-defined shape, a fixed size, or even a definite path through space. They are a far stranger and more beautiful kind of reality. To understand a particle in the quantum world, we must abandon our everyday notions of things and embrace a more fluid, more dynamic, and more interconnected picture. In the language of quantum mechanics, a particle, like an electron or a photon, is not a single, isolated point. It is better understood as a tiny wave-like disturbance, an excitation, a ripple in a more fundamental entity called a quantum field. These quantum fields are not localized. They are spread out across the entire universe, like vast, invisible, and ethereal webs that permeate every inch of space-time. There is an electron field, a photon field, a quark field, a different field for each type of fundamental particle. When we detect a particle, what we are really observing is a localized blip of energy, a concentrated vibration in one of these underlying fields. Imagine a vast, calm ocean. This is the quantum field in its ground state. Now, imagine a single, focused ripple appearing on the surface of this ocean. This ripple is the particle. It is a temporary, localized manifestation of the energy of the underlying field. These quantum ripples, these particles, have properties that seem to defy the rules of common sense. One of the most fundamental of these is superposition. A quantum particle can exist in multiple states or even multiple locations at the same time. It is not that we simply do not know where the particle is. It is that the particle's reality is, in a fundamental sense, spread out over all possibilities. It is like a shadow that is cast in several places at once. It is only when we look, when we make a measurement, that this cloud of possibilities collapses into a single, definite reality. The very act of observation seems to force the particle to make a choice. Another strange quality of these particles is that they do not have a fixed path. When a particle travels from one point to another, it does not follow a single, straight line. Instead, it seems to explore all possible paths simultaneously, its wave-like nature spreading out over all possibilities before it finally settles on a single outcome when it is observed. At this fundamental level, there are no certainties, no definite trajectories, only probabilities. A particle may be more likely to be found in one place than another, but we can never say for sure where it will be until we make a measurement. These quantum fields are not just the source of particles. They are the very canvas upon which our reality is painted. They are the invisible, energetic medium that fills all of space. The infrastructure that allows for the existence and interaction of all the matter and energy in the universe. The forces that govern the cosmos, the electromagnetic force that holds atoms together, the strong nuclear force that binds the nuclei of those atoms, the weak nuclear force that drives radioactive decay, and even gravity itself are all understood in the language of quantum field theory as interactions between these fundamental fields. Let us take a closer look at a field we are all familiar with, even if we are not aware of it, the electromagnetic field. This field is a ubiquitous presence, responsible for the phenomena of electricity, of magnetism, and of light itself. When you turn on a light switch, you are causing a disturbance in this field, a vibration that propagates outwards in the form of photons, the quantum particles of light. These photons travel through space, strike the retina of your eye, and create the sensation of sight. The chair you are sitting on, the screen you are looking at, are held together by the electromagnetic force, a constant exchange of virtual photons between the atoms that make them up. Then there are the other fields, the ones that govern the subatomic world. The electron field gives rise to electrons, the negatively charged particles that orbit the nucleus of every atom and are the basis of all chemistry. The nucleus itself is composed of protons and neutrons, which are, in turn, made up of even more fundamental particles called quarks. These quarks are bound together with incredible strength by the strong nuclear force, which is mediated by the strong field and its associated particles, the gluons. The very stability of matter depends on this powerful, short-range force. All of these fields and the particles that arise from them are described by a single, powerful, and remarkably successful theory known as the Standard Model of particle physics. The Standard Model is a form of quantum field theory, and it is our current, best description of the fundamental constituents of the universe and how they interact. It is a theory that sees the world not as a collection of static, inert objects, but as a dynamic, vibrant, and ceaselessly interacting dance of fields and their excitations. The space you are in right now, the seemingly empty space between you and the walls of your room, is not empty at all. It is a plenum, a rich and complex tapestry woven from the invisible, fluctuating threads of all these different quantum fields. The interactions between these fields are what create the rich and complex world we see around us. Particles are not just born from fields, they also communicate and influence each other through them. When two particles interact, they do so by exchanging other messenger particles, which are themselves excitations of a force-carrying field. For example, when two electrons, both with a negative electric charge, approach each other, they repel. In the language of quantum field theory, this repulsion is understood as the exchange of virtual photons. The electrons are constantly emitting and absorbing these messenger particles, a quantum game of catch that creates the force we perceive as electromagnetic repulsion. This is a profound and beautiful picture. It tells us that forces are not some mysterious, spooky action at a distance. They are the result of a direct, physical exchange of particles, a constant conversation happening at the subatomic level. In the same way, the strong nuclear force that binds quarks together inside protons and neutrons is mediated by the exchange of gluons. And the weak nuclear force, which is responsible for certain types of radioactive decay and for the nuclear reactions that power the sun, is mediated by the exchange of two other types of particles, the W and Z bosons. In this view, particles and fields are two sides of the same quantum coin. The fields are the underlying fundamental reality, the potential for existence. The particles are the manifest, observable reality, the actualized ripples on the surface of this deep energetic sea. The universe is a story of these fields interacting, of their energies being exchanged, of their vibrations giving rise to the beautiful and intricate dance of matter and force that constitutes our world. This is one of the most profound and mind-altering insights of modern physics. It is the realization that the solid, stable, and seemingly inert world of our everyday experience is an illusion. At its core, reality is a fluid, dynamic, and interconnected process, a constant, energetic flux of creation and annihilation, of interaction and transformation. As we continue our journey into the mysteries of the quantum world, we will see how these fundamental concepts of fields, particles, and their strange, counterintuitive behaviors lay the groundwork for an even deeper and more enigmatic understanding of the cosmos. A cosmos that is far more interconnected, far more mysterious, and far more beautiful than our classical intuition could ever have prepared us for. Now, let us delve into one of the most puzzling and essential concepts in all of quantum mechanics, a concept that challenges our very definition of emptiness, the quantum vacuum and its associated zero-point energy. When we think of a vacuum, our intuition, shaped by our classical macroscopic experience, leads us to imagine a space that is completely devoid of everything, no air, no particles, no energy, just pure, absolute nothingness. But in the strange and wonderful world of quantum mechanics, this classical notion of a perfect void is a fiction. Even a space that has been completely emptied of all matter and cooled to absolute zero. The theoretical temperature at which all thermal motion ceases is not truly empty. It is, in fact, a seething, vibrant, and energetic place, a place we call the quantum vacuum. At the heart of this concept lies the ever-present reality of quantum fields. As we have seen, these fields permeate all of space-time, and they are never truly at rest. The uncertainty principle dictates that there will always be a residual, irreducible flicker of motion, a constant, spontaneous bubbling of energy. This minimum possible energy that a quantum field can have, its ground state energy, is not zero. This is the zero-point energy. It is the baseline hum of the universe, the energetic floor below which reality cannot go. To understand how this zero-point energy manifests, we must once again turn to the strange and fleeting world of virtual particles. In the quantum vacuum, the energy is constantly fluctuating, and according to Einstein's famous equation, E equals mc squared, energy and mass are two sides of the same coin. These tiny, transient energy fluctuations can, for an immeasurably short period of time, be converted into a pair of virtual particles, a particle and its antimatter counterpart. These particles pop into existence from the vacuum, exist for a fleeting moment, and then annihilate each other, returning their borrowed energy to the void. We cannot detect these virtual particles directly. Their existence is too brief, too ephemeral, but we can and have measured their collective effects. The Casimir effect is the most famous and direct experimental confirmation of the reality of the quantum vacuum and its zero-point energy. If you take two perfectly flat, uncharged metal plates and place them incredibly close together in a vacuum, you will find that they are pushed towards each other by a mysterious, invisible force. This force arises because the space between the plates restricts the types of virtual particles that can exist there. Only virtual particles with wavelengths that fit neatly between the plates are allowed. The space outside the plates, however, has no such restriction and can host virtual particles of all wavelengths. This creates a pressure imbalance. There are more virtual particles pushing on the outside of the plates than on the inside, and this net pressure is what we measure as the attractive Casimir force. It is a stunning, tangible demonstration that empty space is not empty at all, that the void itself can exert a real physical force. The quantum vacuum and its zero-point energy are not just a source of subtle, microscopic forces. They are a ubiquitous and fundamental aspect of our reality, an invisible backdrop that influences the behavior of all matter and energy in the universe. Although we cannot see or feel this energy directly, its effects are woven into the very fabric of existence. It is a concept that is not just confined to the esoteric world of theoretical physics. It has real, tangible consequences. For instance, the very stability of the atoms that make up our bodies is, in a sense, a consequence of zero-point energy. In the classical, pre-quantum picture of the atom, an electron orbiting a nucleus should be constantly radiating away energy, causing it to spiral into the nucleus in a fraction of a second. The reason this catastrophic collapse does not happen is because the electron, as a quantum particle, is governed by the rules of the quantum vacuum. It cannot simply fall to a state of zero energy. The uncertainty principle dictates that if the electron were confined to the single point of the nucleus, its momentum, and therefore its energy, would be infinitely large. Instead, the electron exists in a stable, ground state orbit, a state of minimum possible energy that is not zero. This ground state is a dynamic equilibrium, a constant dance between the attractive force of the nucleus and the irreducible, zero-point energy of the quantum vacuum, which prevents the electron from ever being truly at rest. The quantum vacuum, in this sense, provides the energetic floor that props up the entire structure of matter. The concept of virtual particles, those fleeting phantoms of the void, is also crucial to our understanding of the fundamental forces of nature. In quantum field theory, as we have seen, forces are mediated by the exchange of messenger particles. But many of these exchanges involve virtual particles. The electromagnetic force between two charged particles, for example, is described as the exchange of virtual photons. These are not real photons that we can detect. They are temporary, off-shell fluctuations of the electromagnetic field, borrowed from the vacuum's zero-point energy for a fleeting moment to carry the message of force between the two charges. The very forces that hold our world together are, in this picture, a constant, ongoing conversation with the creative emptiness of the quantum vacuum. This has profound implications for our understanding of reality. It means that the distinction between something and nothing is not as clear-cut as we might think. Matter and energy are not separate from the void, they are emergent properties of it, temporary, localized excitations of its underlying energetic structure. The universe is not a collection of things existing in space, it is a manifestation of space, a space that is not empty, but is a plenum, a rich and dynamic medium, a sea of infinite potential. The implications of zero-point energy and the quantum vacuum extend from the smallest subatomic scales to the very largest cosmological ones, the early universe. In the first moments after the Big Bang was a realm where quantum effects were dominant, and the energy of the vacuum is thought to have played a crucial and decisive role in shaping the cosmos we see today. The theory of cosmic inflation, which we have explored, posits that the explosive, exponential expansion of the early universe was driven by the immense energy density of a false vacuum state. This is a powerful testament to the creative and world-shaping potential of the void's energy. Furthermore, the tiny quantum fluctuations in this primordial vacuum, the same kind of fluctuations that give rise to virtual particles today, are thought to have been stretched to astronomical scales by the process of inflation. These stretched-in-time fluctuations became the seeds of all cosmic structure. The tiny variations in density that, over billions of years, grew under the influence of gravity to become the galaxies, the clusters of galaxies, and the vast filamentary structure of the cosmic web. We are, in the most literal sense, living inside a macroscopic fossil of the early universe's quantum vacuum. But the influence of the vacuum did not end with the Big Bang. It continues to shape the evolution and the ultimate destiny of our universe. The mysterious dark energy that is causing the expansion of the universe to accelerate is, as we have seen, thought by many to be the modern-day residual energy of the quantum vacuum. The cosmological constant problem, the enormous discrepancy between the theoretical and observed values of this energy, remains one of the greatest unsolved puzzles in all of physics. Its resolution will likely require a deeper, more unified understanding of the relationship between quantum mechanics and gravity. A theory that can explain why the energy of the void is so exquisitely, and fortunately, small. The quantum vacuum is not just a passive, energetic background. It is an active, dynamic, and powerful player in the cosmic drama. It is the source of the forces that bind matter together, the architect of the large-scale structure of the universe, and the engine of its ultimate, accelerating expansion. It is a concept that forces us to completely reevaluate our understanding of space, of energy, and of emptiness itself. The void is not a void, it is a plenum, a sea of potential, a silent but powerful presence that underlies all of existence. And as we continue to probe its mysteries, with our particle accelerators, our space telescopes, and our theoretical inquiries, we are not just exploring a strange corner of physics. We are exploring the very source, the very substance, and the very destiny of our own quantum cosmos. One of the most profound and unsettling consequences of quantum mechanics is the phenomenon of entanglement, a strange and intimate connection that can exist between two or more particles. A bond so deep that it seems to defy our classical intuitions about space, time, and separateness. When two particles, such as a pair of photons or electrons, are created or interact in a specific quantum mechanical way, their individual quantum states can become entangled. This means that from that moment on, they cease to be independent entities and must be described as a single, unified quantum system, even if they are subsequently separated by vast cosmic distances. The strangeness of entanglement becomes apparent when a measurement is made. According to the principles of quantum mechanics, a property of a particle, such as its spin or its polarization, is not determined until it is measured. It exists in a probabilistic superposition of all possible states. But for an entangled pair, the moment you measure a property of one particle, you instantly and definitively know the corresponding property of its distant partner. For example, if two electrons are created with a total spin of 0, and you measure the spin of 1 to be up along a certain axis, you know with absolute certainty that its entangled partner, even if it is on the other side of the galaxy, will be found to have a spin of down along the same axis. It is as if the two particles are engaged in a perfect, instantaneous, and silent conversation, a form of communication that seems to be faster than the speed of light, a clear violation of one of the most sacred principles of Einstein's theory of relativity. Albert Einstein himself was deeply troubled by this aspect of quantum mechanics. He famously and derisively referred to it as spookhafte Fernwirkung, or spooky action at a distance. He believed that this apparent faster-than-light connection was a sign that the quantum theory was incomplete, that there must be some hidden variables, some local, predetermined instructions that the particles carried with them, which would explain the perfect correlation of the measurement outcomes without the need for any spooky, non-local influence. For decades, this was a philosophical debate. But in the 1960s, the physicist John Bell devised a brilliant mathematical theorem, now known as Bell's theorem, which showed that it was possible to design an experiment that could definitively distinguish between the predictions of quantum mechanics and any theory based on local hidden variables. In the decades since, numerous Bell test experiments have been performed with ever-increasing precision and sophistication, and every single one of them has confirmed the predictions of quantum mechanics and ruled out local realism. The spooky action is real. The universe, at its most fundamental level, is non-local. The reality of quantum entanglement has profound and far-reaching implications, not just for physics, but for our entire understanding of the nature of reality. It is crucial to understand, however, that entanglement cannot be used to transmit information faster than light in a controllable way. The outcome of a measurement on one of the entangled particles is fundamentally random. You cannot choose whether you will measure spin up or spin down. You only know that your friend at the other end of the galaxy, upon measuring their particle, will get the opposite result. It is only when you later compare your results, a process that is still limited by the classical speed of light, that you can see the perfect, spooky correlation. Entanglement allows for correlation, but not for communication. And yet, the underlying instantaneous connection is undeniably real. It tells us that our classical picture of a universe made up of separate, independent, and localized objects is a profound illusion. At a deep and fundamental level, the universe is not a collection of things. It is an indivisible, holistic, and interconnected whole. The concept of separateness is an emergent property of our macroscopic world, an approximation that works well for everyday objects, but breaks down completely in the quantum realm. This has deep philosophical and even spiritual resonances. It suggests that the sense of separation we experience as individual beings, the feeling of being a skin-encapsulated ego, as the philosopher Alan Watts called it, is not the ultimate truth of our existence. We are all, in a very real physical sense, entangled with each other, with the planet we live on, and with the cosmos as a whole. The atoms in our bodies were forged in the hearts of stars, their quantum states entangled with the other atoms that were created alongside them. We are literally made of stardust, and we carry within us the entangled history of the universe. Could the more subtle and mysterious aspects of human experience, the profound sense of empathy that can exist between two people? The strange synchronicity of thinking of a loved one just moments before they call. The powerful feeling of collective consciousness that can emerge in a crowd or a ritual be a macroscopic echo of this fundamental quantum entanglement. These are speculative questions, to be sure, and they are far from being scientifically proven, but they are questions that are becoming increasingly legitimate to ask. As our understanding of the quantum nature of biological systems grows, we may find that the brain itself is a kind of quantum information processing system, one that is capable of engaging with the non-local, entangled nature of reality in ways that we are only just beginning to imagine. The practical applications of quantum entanglement are no longer the stuff of science fiction. They are at the heart of the emerging technologies of the 21st century. The field of quantum information science is built upon the idea of harnessing the strange and powerful properties of the quantum world, like superposition and entanglement, to process and transmit information in new and revolutionary ways. We have already touched upon quantum computing, where entangled qubits can be used to perform calculations that are far beyond the reach of any classical computer. But entanglement is also the key to a new and unbreakably secure form of communication, quantum cryptography. The most well-developed of these schemes is called quantum key distribution. In a QKD system, two parties, let's call them Alice and Bob, can generate a shared secret key by exchanging a series of entangled photons. They can then use this key to encrypt and decrypt their messages. The security of this system is guaranteed by the fundamental laws of quantum mechanics. If an eavesdropper, Eve, tries to intercept and measure the entangled photons to learn the key, her very act of measurement will inevitably disturb the delicate entangled state. This disturbance will be instantly detectable by Alice and Bob when they later compare a subset of their measurement results. They will know that their communication channel has been compromised and can discard the key and start over. Unlike classical cryptography, which relies on the computational difficulty of solving certain mathematical problems, the security of quantum cryptography is based on the fundamental principles of nature itself. It is, in a sense, a perfectly secure form of communication. Entanglement is also being explored for its potential in creating new forms of quantum sensing. By creating entangled states of multiple particles, it is possible to build sensors that are far more sensitive than any classical device. For example, entangled photons can be used to create quantum imaging systems that can see objects with a resolution that surpasses the classical diffraction limit of light. Entangled atoms can be used to build quantum clocks that are so precise they would not lose or gain a second in the entire age of the universe. These ultra-precise clocks have applications in everything from fundamental physics tests to next-generation GPS systems. The journey to build these quantum technologies is a long and challenging one. Entanglement is an incredibly fragile and delicate state, easily destroyed by any interaction with the environment. But the progress in the last few decades has been astonishing, and we are now on the verge of a true second quantum revolution, a revolution that will be driven by our growing ability to control and manipulate the strange and beautiful reality of quantum entanglement. It is a revolution that will not just give us faster computers and more secure communication. It will fundamentally change our relationship with the world, allowing us to interact with nature at its deepest, most interconnected, and most mysterious level. The uncertainty principle, with its inherent limit on our knowledge, is not a statement of scientific failure, but a profound and beautiful revelation about the dynamic and creative nature of the universe. It tells us that reality, at its core, is not a static, predetermined machine that can be perfectly known and predicted, but a fluid, vibrant, and endlessly unfolding process. The trade-off between position and momentum, between energy and time, is not a flaw in our theories. It is the very source of all stability and all change in the cosmos. It is the quantum law that prevents the universe from collapsing into a state of perfect, static, and lifeless certainty. This fundamental principle, which governs the behavior of the smallest particles, is also a powerful and insightful metaphor for the nature of our own minds and for the art of living a meaningful and creative life. We often crave certainty. We want to know the future, to control our circumstances, to have a fixed and stable sense of who we are. We want to pin down both our precise position in life, our identity, our status, our place in the world, and our momentum, our direction, our purpose, our path forward. But the uncertainty principle suggests that this is an impossible and perhaps even undesirable quest. The more we try to fix our identity, to cling to a rigid, unchanging sense of self, the more we lose our capacity for growth, for movement, for change. Our momentum becomes uncertain. We become stuck, brittle, and defensive. Conversely, the more we become obsessed with a single, linear path forward, a single goal, a single definition of success, the more we can lose touch with the richness, the complexity, and the beauty of our position in the present moment. We become ungrounded, disconnected from the very source of our own aliveness. A healthy, creative, and fulfilling life, like a stable quantum system, is a dynamic and graceful dance between these two complementary poles. It is a process of finding a balance between the security of being and the adventure of becoming, between the rootedness of our present reality and the open-ended possibility of our future. Sleep is our nightly and natural immersion into this dance of uncertainty. As we drift off, the conscious, controlling, and certainty-seeking mind of the ego relinquishes its tight grip. We let go of our need to know, to define, to predict. We surrender ourselves to the gentle, welcoming embrace of the unknown. And in this surrender, the mind is set free. The rigid, linear tracks of logical thought give way to the fluid, associative, and dreamlike currents of the unconscious. This is the hypnagogic state, the creative, fertile ground between waking and sleeping, a state that has been the source of inspiration for countless artists, scientists, and innovators throughout history. It is a state where the uncertainty is not a problem to be solved, but a creative space to be explored. In the dream state proper, this exploration becomes a full-blown symphony of the imagination. The normal rules of logic, of causality, of time and space are beautifully and playfully suspended. We can be in multiple places at once. We can be different people. We can experience a reality that is built not on the linear logic of cause and effect, but on the deep, associative logic of emotion and symbol. This is not a state of chaos. It is a different, and perhaps more fundamental, kind of order. The uncertainty principle is not a pessimistic statement about the limits of our knowledge. It is a cosmic permission slip, an invitation to embrace mystery, to dance with the unknown, to find peace not in the illusion of control, but in the wise and graceful surrender to the beautiful, unpredictable, and endlessly creative music of an uncertain universe. And every night, as we close our eyes and let go of the day, we are attuning ourselves to this fundamental cosmic rhythm, a rhythm that is the very source of all life, all creativity, and all change. The concept of superposition, the idea that a quantum particle can exist in a multiplicity of states at the same time, is a direct challenge to the either-or logic that governs our classical macroscopic world. It introduces a both-and reality, a reality where contradiction is not a sign of error, but a fundamental feature of existence. This is a concept that is not just confined to the esoteric world of physics. It is a deep and resonant truth about the nature of our own human experience. We are not single, monolithic beings. We are a complex, dynamic, and often contradictory superposition of different selves, different desires, different beliefs, and different potential life paths. We contain, as the poet Walt Whitman wrote, multitudes. The confident self and the insecure self, the compassionate self and the angry self, the adventurous self and the cautious self, all of these and many more coexist within the vast quantum field of our own psyche. We often experience this inner multiplicity as a source of conflict, of indecision, of anxiety. We want both the security of a stable job and the freedom of a creative life. We feel both deep love and profound irritation towards the people closest to us. We hold political or religious beliefs that are, upon closer inspection, full of internal contradictions. We tend to see this as a problem to be solved, a sign of our own inconsistency or lack of integrity. But from a quantum perspective, this inner multiplicity is not a flaw. It is the very source of our richness, our complexity, and our capacity for growth. It is the superpositional nature of our own being. In our waking lives, we often try to resolve this inner tension by identifying with one aspect of ourselves and suppressing or disowning the others. We collapse our rich, complex wave function into a single, coherent, and socially acceptable persona. But the other, unchosen possibilities do not simply disappear. They continue to exist as a latent potential in our unconscious, and they often make their presence known in the strange, symbolic, and multiplicitous world of our dreams. Sleep is the great theater of our inner superposition. As the conscious ego, the director of our waking life, takes a rest, all the other actors in our inner drama are given a chance to come on stage. In our dreams, we can be both the hero and the villain, the victim and the perpetrator, the wise elder and the foolish child. We can experience a reality from multiple perspectives at once. We can live out the consequences of the choices we did not make in our waking lives. This is the psyche's way of exploring its own vast landscape of potential. It is a process of dialogue, of negotiation, of integration between the different and often conflicting parts of ourselves. A dream is not just a random collection of images. It is a holistic, superpositional experience, a complex, multi-layered tapestry of meaning that speaks to the entirety of our being. This is why dreams can be so powerful, so transformative, and so healing. They allow us to access and to integrate the parts of ourselves that we have cut ourselves off from. They remind us that we are more than just the limited, partial identity we present to the world. They invite us to embrace our own inner contradictions, to hold the creative tension of our own multiplicity, and to become a more whole, more integrated, and more compassionate human being. The quantum principle of superposition is not just a strange feature of the subatomic world. It is a deep, psychological, and spiritual truth. It is a truth that we are invited to experience, to explore, and to embrace in the most profound and personal way. In the silent, mysterious, and beautifully superpositional reality of our own sleep. At the heart of quantum mechanics lies the enigmatic figure of the observer, a figure that seems to blur the line between the subjective and the objective, between the mind and the world. The observer effect, the fact that the very act of measuring a quantum system changes its state, is one of the most profound and unsettling discoveries in the history of science. It tells us that we are not detached, passive spectators of a pre-existing reality. We are active participants in a participatory cosmos, a universe that seems to respond to, and to be shaped by, the very act of our observation. The double-slit experiment is the classic demonstration of this. When we are not looking, An electron behaves like a wave, passing through both slits at once. When we look, it behaves like a particle, choosing a single path. Our observation, our inquiry, seems to be a creative act, a force that collapses the ghostly, probabilistic world of quantum potential into the solid, definite world of classical actuality. This is a concept that has deep and powerful implications for our understanding of our own role in the shaping of our reality. The world we experience is not a raw, objective reality that is simply out there. It is a co-created reality, a reality that is born in the interaction between the vast, superpositional potential of the universe and the focused, collapsing power of our own consciousness. Our attention is not a passive spotlight that simply illuminates what is already there. It is a creative force that helps to bring what is there into being. The beliefs we hold, the questions we ask, the quality of our attention, all of these act as a kind of measurement that collapses the wave function of our own experience. If we approach the world with a mindset of fear, of lack, of cynicism, we will tend to selectively perceive and amplify the evidence that confirms that worldview. The world will, in a sense, become the world we expect it to be. If, on the other hand, we can cultivate a gaze of curiosity, of compassion, of appreciation, we can begin to collapse a different kind of reality. A reality that is richer, more beautiful, and more full of possibility. This creative act of observation is not limited to our waking lives. Sleep is a time when the observer turns inward. The lens of our consciousness, which is usually directed at the external, sensory world, turns to face the vast inner landscape of our own psyche. And in our dreams, we are both the creator of the dream world and the observer within it. The landscapes, the characters, the narratives of our dreams are a direct and unfiltered manifestation of our own inner state. But they are not just a passive reflection. The way we interact with the dream, the way we observe it from within, can change its course. In a lucid dream, where we become aware that we are dreaming, this power becomes explicit. We can consciously choose to confront the frightening monster, and in doing so, we may find that it transforms into a helpful guide. We can choose to fly, and in doing so, we collapse the wave function of the dream world in a way that makes flight possible. Lucid dreaming is a powerful training ground for the participatory nature of reality. It teaches us that our awareness is a creative force, that our intention can shape our experience. But even in ordinary dreams, this process is at play. The dream is a constant feedback loop between the unconscious observer and the dream world it is creating. It is a dialogue, a dance. The observer effect is not just a strange quirk of physics, it is a sacred responsibility. It is a call to become more conscious of our own gaze, to recognize its power, and to learn to look at ourselves, at each other, and at the world with a quality of attention that is worthy of the beautiful, mysterious, and participatory cosmos we inhabit. The wave function, the central mathematical object of quantum mechanics, is more than just a tool for calculating probabilities. It is a poetic and powerful map of the hidden, potential nature of reality. It tells us that the universe, at its core, is not a world of solid, definite things, but a shimmering, vibrant sea of possibility. A particle is not a point. It is a wave of potential, spread out in space, containing the possibility of being found here, or there, or anywhere in between. The wave function is the mathematical description of this field of potential. It is the score for the cosmic symphony. A symphony where the notes are not fixed, but are a superposition of all possible tones, waiting to be played. This is a vision of reality that is deeply resonant with our own subjective experience of life. Our lives, too, are a wave function. Our future is not a single, predetermined path, but a superposition of all possible futures. Every moment is a crossroads, a point where the wave function of our life can collapse into a new, definite state, setting us on a new trajectory. The thoughts, the feelings, the desires that flicker through our minds are the ripples on the surface of this deep, potential sea. The what-ifs, the daydreams, the imagined scenarios. These are not just idle fantasies. They are the exploration of our own personal wave function, the tracing of the different, possible paths that our lives could take. And sleep is the time when we dive most deeply into this ocean of possibility. In the waking state, our consciousness is largely a collapsed wave function. We have made our choices. We are on our path. Our reality is, for the most part, definite and singular. But as we fall asleep, the collapse is undone. We decohere from the classical world and re-enter the quantum realm of pure potential. In our dreams, we are no longer bound by a single reality. We can experience a multitude of possibilities simultaneously. A dream is not a linear narrative, it is a holistic, superpositional experience, a cross-section of our own personal wave function. It can contain echoes of the past, premonitions of the future, and symbols of our deepest, timeless nature, all woven together in a single, multi-layered tapestry of meaning. To interpret a dream is to act as an observer, to collapse its rich, superpositional meaning into a single, conscious understanding. But the dream itself, in its raw, uninterpreted state, remains a pure expression of possibility. It is a reminder that our reality is not as fixed and solid as it appears. It is a reminder that we are always, at every moment, standing at the edge of an infinite sea of potential. The wave function is the universe's most beautiful and profound poem. It is a poem written in the language of mathematics, a poem that speaks of a reality that is not made of things, but of possibilities, not of certainties, but of dreams. And every night, as we close our eyes and surrender to the gentle, wave-like currents of our own consciousness, we are given the chance to read a few more lines of this endless cosmic verse, and to remember the deep, beautiful, and liberating truth of our own infinite potential. The universe, as described by modern physics, is a story of two grand and seemingly incompatible narratives. On the one hand, we have Einstein's theory of general relativity, the story of the large-scale cosmos, a world of smooth, curved space-time, of galaxies and black holes, a world governed by the elegant, deterministic laws of gravity. On the other hand, we have quantum mechanics, the story of the small-scale world, a world of discrete particles, of probabilistic jumps, of uncertainty and superposition. These two theories are the twin pillars of modern physics, and each has been confirmed with unprecedented accuracy in its own domain. But they do not seem to speak the same language. They are based on fundamentally different principles and mathematical formalisms. Finding a single, unified theory that can encompass both a theory of quantum gravity is the single greatest challenge in all of theoretical physics. It is the Holy Grail, the quest to find the single, underlying law that governs the entire cosmos, from the subatomic to the cosmological. This tension between the large and the small, the continuous and the discrete, the deterministic and the probabilistic, is not just a problem for physicists. It is a tension that we all live with, a fundamental duality of our own experience. We live in the macroscopic, classical world of our bodies, a world governed by the seemingly predictable laws of gravity and motion. But our minds, our consciousness, often seem to operate on a different logic, a logic that is more akin to the quantum world, a world of fluid associations, of nonlinear time, of superpositional states. Sleep is the realm where this tension between the two worlds is most acutely felt, and perhaps where a bridge between them can be found. As we fall asleep, our consciousness detaches from the classical sensory world and enters a state that is deeply quantum-like. In our dreams, the normal laws of physics are suspended. We can fly, defying gravity. We can pass through walls, an act of macroscopic quantum tunneling. We can be in multiple places at once, a direct experience of superposition. The scale of our experience becomes fluid and dynamic. In one moment, we can feel as vast as a galaxy, our consciousness expanding to fill the cosmos. In the next, we can feel as small and insignificant as a single grain of dust. This constant shifting of scale, this effortless movement between the macro and the micro, is a hallmark of the dream state. It is as if our dreaming mind is a natural quantum gravity simulator, a place where the rigid distinctions between the large and the small dissolve, and a more unified, holistic reality is experienced. Could it be that the structure of our own consciousness is a clue to the structure of the universe? Could the way our minds bridge the gap between the concrete, physical world and the abstract, symbolic world of thought be a reflection of the way that nature bridges the gap between gravity and the quantum? This is a speculative but deeply compelling idea. It suggests that the answers to the deepest questions of physics may not just be found in particle accelerators or space telescopes, but also in the deep, introspective exploration of our own inner worlds. Sleep, in this view, is not just a biological function. It is a nightly journey to the very frontier of our understanding, a place where the two great warring narratives of the universe can meet, can dance, and can perhaps, in the symbolic, poetic language of our dreams, find a way to become one. The unresolved tension between gravity and the quantum is not just a problem for science. It is the central, creative tension of our own human existence, a tension that we are invited to explore, to hold, and to integrate in the deep, mysterious, and unifying space of our own sleep. In the final analysis, the deepest mystery that the quantum world presents us with is not about particles or waves, but about ourselves. The journey into the heart of the atom has led us unexpectedly to the threshold of our own consciousness. The discovery that the observer is not a detached spectator, but an active participant in the creation of reality, has forced science to confront a question it has long sought to avoid: what is the nature of the observer? What is this thing we call consciousness that seems to hold such a privileged and powerful place in the cosmic drama, the classical materialistic worldview, which has dominated science for centuries, sees consciousness as an epiphenomenon, a secondary and accidental byproduct of complex neural computation in the brain. It is a ghost in the machine, a strange and wonderful illusion, but ultimately not a fundamental aspect of reality. But the quantum world seems to hint at a different, more radical possibility. It suggests that consciousness may not be a late-coming accident in a dead, mechanical universe, but may be a fundamental, irreducible, and perhaps even primary aspect of the cosmos itself. This is the central tenet of a philosophical position known as panpsychism. The idea that consciousness, in some rudimentary form, is a property of all matter. In this view, an electron does not just have mass and charge, it also has a tiny, primitive flicker of subjective experience. As matter becomes more complex and organized, as in a living cell or a human brain, this rudimentary consciousness can combine and complexify, giving rise to the rich, self-aware consciousness that we experience. This is a staggering idea, one that completely inverts our normal understanding of the world. It suggests that the universe is not a collection of dead matter that somehow, miraculously, gives rise to consciousness. It suggests that the universe, from its very beginning, has been imbued with a potential for awareness, and that we, as conscious beings, are not a strange anomaly, but a natural and beautiful expression of this fundamental cosmic property. In this worldview, the quantum field is not just a field of energy and potential, it is also a field of nascent consciousness. The entire universe is a single, vast, and interconnected mind, and our individual consciousnesses are like eddies in this great cosmic stream. This is a vision that has been expressed in different forms by mystics and philosophers for millennia, the Brahman of the Vedanta, the mind of God of the Hermetic traditions, the anima mundi of the Platonists. These are all expressions of the same deep intuition that consciousness is the ultimate reality. What is new is that this ancient spiritual intuition is now finding a tentative but growing resonance with the cutting edge of modern physics. The puzzles of the quantum world, the observer effect, entanglement, the nature of time may all be clues that are pointing us towards a new, post-materialist paradigm. A paradigm that recognizes the fundamental role of consciousness in the structure of reality. And sleep, once again, becomes our most intimate and direct portal to this deeper reality. As the conscious individual ego dissolves, we are given the chance to merge back into the universal field of consciousness from which we arose. The dream state, with its symbolic language, its non-local connections, and its creative power, may be a direct experience of the mind of the universe, expressing itself through the unique filter of our own personal history. To fall asleep is to remember our cosmic origins. It is to let go of the illusion of our own separateness and to reunite with the single, unified, and conscious field that is the source of all being. We are not just in the universe. The universe is in us. We are the universe's way of knowing itself, of feeling itself, of dreaming itself into existence. And the greatest secret of the quantum world may be a secret that we have known all along, in the deepest, most silent, and most sacred chambers of our own conscious hearts. The strange, paradoxical, and beautiful world of quantum mechanics is not a distant, abstract realm of interest only to physicists. It is the very ground of our being, the invisible, energetic, and conscious foundation upon which our entire reality is built. The principles of superposition, of uncertainty, of entanglement, are not just descriptions of subatomic particles. They are deep, resonant metaphors for the nature of our own minds, our own lives, our own souls. The universe that the quantum revolution has revealed is not a cold, dead and deterministic machine, but a living, breathing, and participatory cosmos. A universe that is constantly being co-created in the dance between potential and actuality, between the observer and the observed. And sleep, the state we enter every night, is our most profound and direct access to this quantum reality. It is a nightly pilgrimage to the source, a journey into the superpositional sea of our own consciousness, a surrender to the creative uncertainty of the void, an immersion in the entangled web of our own interconnectedness. To understand the quantum world is to understand ourselves in a new and deeper way. It is to recognize that we are not fixed, solid, and separate entities, but fluid, multi-layered, and deeply connected beings. It is to embrace the paradox of our own nature, to honor both the particle of our individual existence and the wave of our universal connection. It is to find a new kind of freedom, a freedom that comes not from control, but from surrender, a freedom that is born from the recognition that at the heart of reality lies not a rigid certainty, but an infinite, creative, and beautiful mystery. The journey into the quantum realm is a journey home, a journey back to the fundamental, magical, and dreamlike nature of our own true being. And every night, as we close our eyes and drift into the gentle, quantum sea of sleep, we are given the chance to remember, to heal, and to be reborn. In the vast tapestry of human knowledge, there lies a remarkable journey that began with a simple, audacious dream. Once it was said, in ages long past, that a single, brilliant mind could grasp the entirety of human understanding, could hold the sum of all knowledge within its grasp. Today, as we stand amidst an unprecedented explosion of information, a deluge of data that doubles in volume every few years, we might be tempted to wonder if such a grand, unified comprehension is still possible, or if it has become a relic of a simpler, more naive time. But this story is not about the quantity of knowledge, about the endless accumulation of facts and figures. It is about something far more profound, something that speaks to the very heart of the human quest for meaning, the quality of our understanding. Consider the cosmos that surrounds us, a universe of almost unimaginable scale and complexity. We know that there are hundreds of billions of galaxies, each containing hundreds of billions of stars. We have identified millions of species of life on our own small planet, with millions more likely waiting to be discovered. The sheer volume of information is staggering. To memorize the precise position and velocity of every planet, to catalog the intricate details of all 600,000 known species of beetles, this would be a task beyond the capacity of any single mind, or even any supercomputer we could currently conceive. But true understanding, the kind of deep, explanatory knowledge that is the hallmark of scientific progress, does not require this. It does not seek to grasp every particular, but to uncover the general, underlying principles that govern reality itself. It is the search for the simple, elegant rules that give rise to the complex, beautiful world we see around us. This quest for deep explanatory principles is perfectly illustrated by the revolution in our understanding of gravity. For millennia, humanity observed the motions of the planets, cataloging their positions with meticulous care. This was knowledge, but it was a descriptive, predictive knowledge. It could tell you where Mars would be in the sky on a given night, but it could not tell you why. Then came Isaac Newton, who, with his law of universal gravitation, provided a single, powerful principle that could explain not just the motions of the planets, but also the fall of an apple and the ebb and flow of the tides. This was a profound leap in understanding, but even Newton's theory, as powerful as it was not the final word. It described gravity as a mysterious force acting at a distance. But it did not explain the mechanism of this force. It was Albert Einstein who, with his general theory of relativity, provided the next, deeper layer of explanation. Einstein showed us that gravity is not a force at all, but is the very curvature of space-time itself. A dynamic, four-dimensional fabric that is bent and warped by the presence of mass and energy. Planets do not move in their orbits because they are being pulled by an invisible force from the sun. They move in straight lines through a space-time that has been curved by the sun's mass. This is a far more profound and beautiful explanation. It does not just tell us what will happen, it reveals why it happens, giving us an insight into the very structure of reality. And this is the crucial point: prediction alone, no matter how accurate, is not the same as understanding. Imagine, for a moment, that we possessed a magical oracle, a super predictor capable of answering any question about the outcome of any possible experiment. We could ask it, if I build this bridge in this way, will it stand? And it would give us a definitive yes or no. This would be an incredibly powerful tool, but it would not be a substitute for understanding. We would still need the principles of engineering, the knowledge of material science, the understanding of stresses and strains, to design the bridge in the first place. The oracle could tell us if our spaceship design would successfully reach the stars, but it could not design the spaceship for us. Understanding is what bridges the gap between knowing that and knowing why. It is what allows us to innovate, to create, to solve new problems that we have never encountered before. This is a pattern we have seen repeat itself throughout human history. The master builders of the ancient world, the constructors of the great cathedrals and pyramids, relied on a vast and complex set of rules of thumb, traditions, and accumulated experience, passed down through generations of apprenticeship. Their knowledge was deep, but it was also narrow, limiting them to familiar designs and incremental improvements. Today's architects and engineers, armed with a deeper, more unified understanding of the fundamental principles of physics and materials, can create structures that the ancients could hardly have imagined, from soaring, impossibly thin skyscrapers to orbiting space stations. This remarkable progress did not come from accumulating more rules, but from developing a smaller number of more general, more powerful, and more deeply explanatory principles that work everywhere, from the Earth to the Moon and beyond. As our knowledge grows, we witness a profound and beautiful paradox, a tension between two opposing forces. On the one hand, the ever-increasing breadth of what we know, the sheer volume of information pushes us towards specialization, the biologist, the physicist, the historian. The artist each delves deeper into their own specific corner of the vast tapestry of knowledge. It can seem as though the dream of a unified understanding is receding, that we are destined to become a species of experts who know more and more about less and less. But on the other hand, there is a countervailing force, a force that is, I believe, ultimately more powerful. It is the drive towards unification, the discovery that, as our understanding deepens, seemingly disparate phenomena are revealed to be different manifestations of a single underlying reality. And in this great intellectual battle between the fragmentation of specialization and the unification of deep understanding, depth is winning. Consider the history of mathematics. The ancient Babylonians and Egyptians had a vast and sophisticated knowledge of arithmetic and geometry, but it was a collection of separate techniques and rules for specific problems. The ancient Greeks, with their invention of the axiom, a geometric method, began the process of unification, showing how a vast number of geometrical truths could be derived from a small number of self-evident axioms. Today, modern mathematics, with its abstract structures of groups, fields, and topologies, contains within it all the understanding of these ancient systems, but in a far clearer, more powerful, and more unified form. The same story can be told in the history of cosmology. The Ptolemaic system, with its complex machinery of epicycles and deferents, was a masterpiece of predictive astronomy, but it was a collection of ad hoc rules, one for each planet. When Nicholas Copernicus placed the Sun at the center of the solar system, he did not just propose another theory. He radically simplified our understanding, revealing a deeper, more elegant underlying order. When Michael Faraday and James Clerk Maxwell unified the seemingly separate forces of electricity and magnetism into a single theory of electromagnetism, they showed us that apparent differences on the surface often mask a deeper, underlying unity. This same transformative process is happening today in the field of medicine. Where once doctors relied on a vast catalog of specific treatments for specific diseases, we are now beginning to understand the common underlying molecular and genetic mechanisms that connect seemingly different conditions, from cancer to heart disease to neurodegenerative disorders. This deeper, more unified understanding is what allows for the development of truly novel and powerful treatments. Therapies that target the root cause of disease, not just its symptoms. What we are witnessing across all these fields is not just the accumulation of knowledge, but its transformation. It is like the process of streams flowing into rivers and rivers flowing into a great, unified ocean. Our understanding of the world is becoming more coherent, more interconnected, more unified. We are not, as it might seem, moving further away from a state of overall comprehension. We are moving closer to it. This does not mean that we will one day know everything there is to know. The universe is likely to be infinitely complex, and there will always be new frontiers to explore, new mysteries to uncover. But it does mean that we are approaching a point where the structure of our knowledge itself is becoming more unified. We are beginning to glimpse the outlines of a truly fundamental theory, a theory that could provide a single, coherent explanatory framework for all of reality. This journey towards a more unified understanding is leading us towards something truly remarkable, something that has been the dream of physicists and philosophers for centuries, a true theory of everything. But this is not just a quest to unify the four fundamental forces of physics, as it is often portrayed. It is not just about finding the single, underlying principle that governs the dance of particles and waves. It is about something far grander, far more profound. It is about arriving at a unified understanding of reality itself. A framework that can accommodate not just the physical world, but also the nature of knowledge, of computation, and of life. This ultimate theory will not and cannot explain every single detail of existence. It will not predict the outcome of every human choice or the precise shape of every snowflake. That level of detail is likely beyond the reach of any finite explanation. But what it will do is show us how all our different explanations, from the laws of quantum mechanics to the principles of biological evolution, from the nature of computation to the growth of knowledge, fit together. It will reveal the deep underlying connections that bind all these different aspects of reality into a single, coherent, and comprehensible whole. It will be a theory that explains the reach of our scientific laws, the very comprehensibility of the universe itself. As we look up at the night sky, we are no longer just seeing points of light in the darkness. Through the lens of our current, partial understanding, we are already beginning to see a much richer and more interconnected reality. We see the complex, beautiful dance of gravity shaping the curvature of space-time. We see the life cycles of stars, from their birth in dusty nebulae to their explosive deaths as supernovae, a process that forges the very elements that make up our bodies. We see the fundamental forces of nature at play, the same forces that govern the interactions of particles in our laboratories, writ large on a cosmic scale. Each new discovery, each new piece of the puzzle, does not just add another isolated fact to our collection. It helps us to see the whole picture more clearly. It illuminates the connections. It reveals the deeper patterns. It brings us one step closer to a truly unified vision. We are living in a remarkable moment in the history of human thought, a moment where the depth of our knowledge is beginning to reveal the profound, underlying unity of all things. This is not the end of the journey of discovery. It is, in a sense, the end of the beginning. It is the dawn of a new way of seeing, a new way of understanding, a new way of being in the world. As we continue to explore the cosmos, both outward into the vastness of space and inward into the deep structure of our theories, we are not just gathering more information. We are uncovering the deep, beautiful, and intricate connections that bind everything together in the grand, cosmic dance of existence. In this journey towards a unified understanding, we are discovering that knowledge is not just about accumulating facts, but about seeing the patterns that connect them. Just as Einstein showed us that space and time are not separate, but are woven together into a single, dynamic fabric. Just as he showed us that matter and energy are not distinct, but are two faces of the same fundamental coin. Our growing understanding of reality is revealing itself to be a single, interconnected tapestry. Through this lens, the cosmos becomes not just a random collection of objects and events, but a coherent and deeply meaningful story. A story written in the universal language of mathematics and physical law. And as we stand at this unique vantage point, looking both backward at the long history of our quest for knowledge and forward to the mysteries that still lie ahead, we can see that our journey is not taking us further away from a state of ultimate comprehension, but for the first time in human history, bringing us tantalizingly, breathtakingly close. The future holds not just more knowledge, but deeper insight. Not just more information, but greater understanding. And in this cosmic dance of discovery, we are learning not just about the universe, but about the very nature of understanding itself. The vast, unending expanse of space offers us a landscape of mysteries that have captivated and bewildered humanity for generations. We have, in the grand scheme of things, explored only the tiniest, most infinitesimal fraction of its secrets, and yet, this exploration holds the key not just to understanding the cosmos, but to understanding the very process by which we make sense of the universe we inhabit. Science is our greatest and most powerful tool for unraveling these cosmic mysteries, a tool that is not static and rigid, but is itself shaped by a profoundly dynamic, iterative, and evolutionary process. What propels us forward in our quest for knowledge is not the comfort of certainty, but a relentless, insatiable drive to replace our current, incomplete answers with better, deeper, and more powerful explanations. The journey of scientific discovery is rarely a straightforward, linear march towards truth. It is more like the exploration of a vast, uncharted territory, a complex and interconnected web of questions, experiments, and theories that are constantly evolving, adapting, and interacting with each other. A new scientific theory often emerges not from a vacuum, but from a crisis. A moment when our current explanations fail to account for new, unexpected observations. Imagine being in a dark, sealed room with only a few thin cracks of light streaming in. Each new discovery is like finding a new crack, letting in a little more light, revealing a small, new part of the much larger picture that lies outside. But each new sliver of light does not just provide answers. It also reveals new and more profound questions. The goal of every scientific endeavor, from the smallest laboratory experiment to the grandest cosmological theory, is not simply to collect and catalog observations. It is to develop better and deeper explanations for what we see, and perhaps even more importantly, for what we do not yet fully understand. The process by which we cultivate this knowledge, the very methodology of science, is an iterative and evolutionary one. It begins with the identification of a problem, a gap in our current understanding, a phenomenon that our existing theories cannot explain. This is the creative spark, the moment of curiosity that ignites the scientific process. From this problem, new ideas, new conjectured solutions, or hypotheses, are born. These are bold, imaginative, and often unjustified guesses about how things might really work. They are the raw material of scientific progress. But an idea, no matter how beautiful or elegant, is not enough. It must be subjected to the fire of rigorous testing and, most crucially, of criticism. In this process, weaker models, those that fail to solve the problem or that create even more problems, are discarded. Stronger, more robust, and more deeply explanatory models survive, but they do not survive unchanged. They are refined, adapted, and improved in the light of criticism and new evidence. This is not a failure of the process, it is its greatest strength. Paradoxically, this process of trial and error often requires us to backtrack, to abandon a promising but ultimately flawed idea, to admit that we were wrong. Progress in science is not always a straight, forward march. It is a winding and sometimes recursive journey. It is a process of building, of testing, of demolishing, and of rebuilding, always on a stronger and more solid foundation. Criticism is the lifeblood of this scientific process. It is the selective pressure that drives the evolution of our knowledge. And contrary to the popular textbook image of science, The most important form of criticism does not come from experimental results. An experiment can tell us that a theory's prediction is wrong, but it cannot, by itself, tell us why it is wrong, or what a better explanation might look like. The most powerful and productive form of criticism comes from a direct, logical, and philosophical challenge to the explanations that a theory provides. When a new theory is proposed, it is not enough for it to simply fit the existing data. It must solve the problems that its predecessor could not. It must provide a deeper, more coherent, and more satisfying explanation of reality. A theory that cannot withstand this kind of rigorous, intellectual scrutiny, a theory that is vague or ad hoc, or that creates more puzzles than it solves, will ultimately be rejected. Not because an experiment has falsified it, but because it is a poor explanation. This brings us to a crucial aspect of what makes a scientific theory good. It must be falsifiable. A theory that can explain everything, that can be twisted and tweaked to fit any possible observation, is not a scientific theory. It is a dogma. A good scientific theory makes bold, specific, and risky predictions. It sticks its neck out. It exposes itself to the possibility of being proven wrong. It is this very vulnerability, this openness to being refuted, that is the source of science's strength. The theories that survive this relentless process of attempted falsification, the theories that withstand the fire of criticism, are the ones that we can provisionally accept as our best current understanding of reality. This view of science, championed by the philosopher Karl Popper, is a powerful antidote to the older and still common idea of inductivism. Inductivism is the notion that scientific knowledge is built by accumulating a large number of observations and then extrapolating a general law from them. It is the idea that we move from the specific to the general, from the observed to the unobserved. But this process is logically flawed, as the philosopher David Hume pointed out centuries ago. Just because the sun has risen every day in the past, we have no logical guarantee that it will rise tomorrow. The future does not have to resemble the past. Popper's solution was to turn this process on its head. Science does not proceed by induction, but by deduction. We do not start with observations. We start with problems, with bold, creative conjectures. We then use observation and experiment not to prove our theories, but to test them, to try and falsify them. The theories that survive this process are not proven to be true, but are corroborated, meaning they have, so far, withstood our best attempts to knock them down. They are our best and most resilient explanations. In this sense, science is driven not by the accumulation of data, but by the relentless pursuit of better, deeper, and more hard-to-vary explanations of reality. The evolution of our scientific knowledge bears a striking resemblance to the process of biological evolution by natural selection. Just as different species compete for resources in an ecosystem, different scientific theories compete for explanatory power in the intellectual landscape of a particular field. Some theories, like the dinosaurs, are dominant for a time, but are eventually driven to extinction by a new, more powerful competitor. Other theories adapt. They evolve. They are refined and modified in the light of new evidence and criticism. New theories are constantly emerging, born from the creative, mutational process of human imagination. And they are then subjected to the harsh, selective pressure of experimental testing and critical debate. The theories that survive and thrive are the ones that are fitter, the ones that are better suited to explaining the mysteries of the universe that eluded their predecessors. This evolutionary nature of knowledge ensures that science is not a static, dogmatic system of belief. It is a dynamic, open-ended, and constantly improving process. It is a process of trial and error, of conjecture and refutation, played out on a grand, intellectual scale. It is a process that mirrors the very creativity and resilience of life itself. Experimentation. In this evolutionary picture plays a crucial but perhaps secondary role. Its primary function is not to generate theories, but to act as a harsh and impartial judge, a selective environment that can kill off a bad theory. The most elegant and robust theories often make bold, surprising, and highly specific predictions, laying out scenarios that can be meticulously tested in the laboratory or through astronomical observation. A single, definitive experimental result that contradicts a theory's prediction can be enough to falsify it, to send it to the dustbin of scientific history. But a correct prediction, while valuable and often celebrated, does not and cannot definitively prove a theory to be true. There could always be another, as yet unthought of, theory that makes the same prediction but provides a deeper and more satisfying explanation. The true value of a correct prediction is that it lends a theory a greater degree of corroboration, of resilience. It is a sign that the theory is on the right track, that it has captured some real aspect of the structure of reality. But it is not the final word. The experiments are the stepping stones, not the destination. They are the fuel for the ongoing search for ever deeper and more comprehensive explanations. At the heart of all scientific progress, then, lies this relentless search for better explanations. A good explanation is not just one that accurately fits the observable data. A complex, ad hoc theory with enough free parameters can be made to fit any set of data. A good explanation is one that is also simple, elegant, hard to vary, and has a broad reach. It should explain more than it was designed to, making new, surprising, and testable predictions. Theories that fail to provide this kind of deep, explanatory power, no matter how accurately they might predict a particular phenomenon, will ultimately be seen as inferior, as mere phenomenological models, not as fundamental theories of reality. Science advances not simply by adding new facts to the great encyclopedia of what we know, but by fundamentally rewriting the encyclopedia, by replacing old, weak ideas with new, more powerful ones that offer a deeper and more profound insight into the mysteries of the universe. The search for knowledge, in this evolutionary and explanation-driven picture, is not a journey with a final destination. There is no ultimate, final truth with a capital T waiting for us at the end of the scientific road. Each new breakthrough, each new layer of understanding, does not lead to a final, complete answer. Instead, it opens up a new vista of questions, a new landscape of ignorance that was previously invisible to us. Today's best theory is simply tomorrow's stepping stone. The standard model of particle physics, for example, is an incredibly successful theory, but it leaves a host of deep questions unanswered. Why do the fundamental particles have the masses they do? What is the nature of dark matter and dark energy? How can we incorporate gravity into a quantum framework? Each of these questions represents a new frontier, a new problem that is driving the next generation of scientific research. This open-ended, unending nature of the scientific quest is not a sign of failure. It is the very source of its vitality and its excitement. It is what keeps science a living, breathing, and constantly evolving enterprise, rather than a static, dogmatic set of revealed truths. The universe, in all its vastness and complexity, is a landscape of infinite possibility. And the human mind, with its unique capacity for creative conjecture and rational criticism, is the perfect tool for exploring it. The cosmos challenges us to think beyond what we currently know, to question our most deeply held assumptions, to constantly strive for a better, deeper, and more unified understanding. It reflects back to us the very nature of science itself, a system built not on the solid ground of certainty, but on the dynamic, ever-shifting landscape of possibility. Each new discovery, from the subatomic to the cosmological, does not just add to our knowledge of the external world, It also deepens our understanding of ourselves, of our place in the cosmos, of the very nature of existence. As we explore the universe, we are also exploring the outer limits of human potential, the remarkable capacity of a small, curious primate on a tiny planet to grasp the deep, elegant, and often counterintuitive laws that govern the whole of reality. It is a journey that connects us to the universe in the most profound way possible, not just as its inhabitants, but as its conscious, questioning, and self-aware partners in a grand and unending dance of discovery. As we stand and gaze up at the night sky, at the vast, silent emptiness punctuated by the distant, twinkling lights of stars, we are confronted with one of the most fundamental questions of all. How do we know that what we are seeing is real? How can we be sure that the universe out there is not just an elaborate illusion, a grand and beautiful projection of our own minds? This is not just a question for late-night philosophical debates. It is a question that lies at the very heart of the scientific enterprise. Before we can even begin to build our theories of the cosmos, we must first have some confidence that there is a real objective cosmos to be theorized about. The first step on this journey is to understand the nature of explanations themselves. In science, an explanation is not a process of justifying a belief by tracing it back to some ultimate, infallible authority, whether that be a sacred text, a philosophical principle, or a direct, unmediated sensory experience. The long and often painful history of human thought has shown us that the search for such an ultimate, authoritative justification is a dead end. There is no such source. All our knowledge is, and always will be, conjectural, tentative, and open to revision. Instead, a scientific explanation is evaluated by its ability to solve problems, to make sense of the world, and to withstand rigorous criticism. An explanation does not need to be justified by its origin. It must justify itself by its performance. It must hold up under the relentless fire of logical scrutiny and experimental testing. This is the beauty and the power of the scientific method. It is not a quest for certainty, but a quest for the best, most resilient, and most deeply explanatory ideas. With this understanding of explanation in hand, we can begin to tackle the challenge of solipsism. Solipsism is the philosophical idea that only one's own mind is sure to exist. Everything else, the external world, other people, the entire universe could be nothing more than a dream, a figment of one's own, solitary consciousness. It is an idea that is logically irrefutable. You can never, with absolute certainty, prove that you are not the only mind in existence, and yet it is an idea that collapses under the weight of its own radical skepticism. To take solipsism seriously is to abandon the very possibility of knowledge, of science, of communication, of a shared reality. Our entire lives, our every action, our every thought, are predicated on the tacit assumption that there is a real objective world that exists independently of our own minds. Imagine trying to design and build a bridge while sincerely believing that the laws of physics and the properties of steel are just a projection of your own imagination. The endeavor would be not just impossible, but nonsensical. Scientific reasoning, by its very nature, is a rejection of solipsism. It is a collaborative, public enterprise that is built on the shared assumption that there is a real objective and comprehensible universe that we can all investigate, that we can all build theories about, and that we can all argue about. The very possibility of a scientific debate presupposes a shared reality to be debated. But even if we reject solipsism and accept the existence of an external reality, we are still faced with the challenge of observation and the problem of induction. How can we be sure that our senses are giving us a reliable picture of the world? And how can we justify our belief that the patterns we observe in the past will continue to hold in the future? The problem of induction, most famously articulated by the philosopher David Hume, is the puzzle of why we believe that repeated observations can lead to a general law. Just because every swan we have ever seen is white, we have no logical guarantee that the next swan we see will not be black. Just because an apple has fallen from a tree every single time in the past, we cannot, with absolute certainty, prove that it will do so tomorrow. The philosopher Karl Popper offered a brilliant and powerful solution to this long-standing problem. He argued that science does not and cannot proceed by induction. We do not build our knowledge by accumulating observations and then generalizing from them. Instead, science progresses through a process of conjecture and refutation. We start with a problem. We propose a bold, creative, and falsifiable explanation. And then we subject that explanation to the most rigorous tests we can devise, not to confirm it, but to try and refute it. The theories that survive this process, the ones that have withstood our best attempts to knock them down, are the ones we provisionally accept as our best current understanding of reality. Science is not about proving things to be true beyond all doubt. It is about eliminating error, about choosing the theory that has, so far, survived criticism better than its rivals. This brings us back to the question of reality itself. In this Popperian, explanation-driven view of science, reality is not an absolute, fixed concept. It is a judgment, a status that we confer upon those entities and phenomena that are part of our best, most resilient, and most deeply explanatory theories. The concept of gravity was once thought to be a mystical, occult force pulling objects downwards. Newton's theory gave it a new, more real status as a universal, mathematical force. Einstein's theory gave it an even deeper reality, reframing it as the curvature of spacetime. What we consider to be real evolves as our explanations improve. But there is a practical common sense aspect to this as well. The 18th century writer and wit, Dr. Samuel Johnson, famously responded to the philosophical idealism of Bishop Berkeley, who argued that matter does not exist independently of the mind, by kicking a large stone and declaring, "I refute it thus." His point was simple and profound. Reality is that which kicks back. If something can act upon us, if it can resist us, if its behavior requires an independent explanation that goes beyond our own internal, subjective experience, then we have good reason to consider it real. Galileo used this same principle to argue for the reality of Jupiter's moons. The light from those moons was not just a passive image. It was an active, physical entity that interacted with his telescope and his eye in complex and predictable ways. The moons kicked back, and in doing so, they asserted their own independent reality. Science applies this kicking back principle at every level of its inquiry. We believe electrons are real, not just because our theories require them, but because we can see their tracks in a cloud chamber. We can manipulate them with magnetic fields. We can use their flow to power our cities. They are not just theoretical constructs, they are entities that have a rich, complex, and autonomous set of effects on the world. This is the crucial distinction between a real entity and a mere illusion or a mental construct. A reflection in a mirror, for example, is complex, but its complexity is not its own. It is borrowed entirely from the object it is reflecting. It has no autonomy. A planet, on the other hand, has a vast and intricate complexity that is entirely its own, its geology, its atmosphere, its history. It exists and evolves independently of our observation of it. The more complex and autonomous an entity is, the more it kicks back, the more reason we have to consider it real. And this is where the evolutionary nature of our understanding comes full circle. Our scientific explanations do not just help us to uncover a pre-existing reality. they also change what we are capable of perceiving as real in the first place. The concept of a quantum field, for example, was once a strange and abstract mathematical tool. But as our theories have developed, and as we have seen its effects in a vast range of experiments, from the Casimir effect to the behavior of particles in accelerators, it has acquired a new and profound reality. It is now seen as the fundamental, underlying substance of the cosmos. This process is never-ending. The history of science is a history of our concept of reality becoming deeper, richer, and stranger. Dark matter and dark energy are the current enigmas on this frontier. They are currently hypothetical entities, inferred from their gravitational effects on the things we can see. But as our observations and our theories improve, they may one day transition from being mysterious dark entities to being accepted, and perhaps even understood components of our reality. The criteria for what we consider to be real are not fixed. They are open-ended and constantly improving, driven by our relentless quest for better, deeper, and more powerful explanations. It is a journey that is not about arriving at a final, absolute truth, but about a continuous process of peeling back the layers of reality, with each new layer revealing a world that is more complex, more beautiful, and more wonderfully mysterious than the one before. To understand the universe, we must first understand the nature of the tools we use to build our knowledge. And the primary tool of science is not observation, but explanation. This is a subtle but crucial distinction. The traditional view of science, known as inductivism, sees knowledge as arising from the patient accumulation of repeated observations. We see the sun rise in the east every day, and from this we induce the general law that the sun always rises in the east. But this is a deeply flawed picture of how science actually works. It does not explain why the sun rises, and it provides no logical guarantee that it will do so tomorrow. It is a form of prediction, not understanding. The philosopher of science, Karl Popper, provided a revolutionary alternative to this view. He argued that science does not progress by confirming theories, but by refuting them. We start not with observations, but with problems, with puzzles that our current understanding cannot explain. We then propose bold, creative, and highly specific conjectures, new theories that attempt to solve these problems. The crucial feature of a scientific conjecture is that it must be falsifiable. It must make risky predictions that, if they turn out to be wrong, would force us to abandon the theory. We then subject these theories to the most rigorous tests we can devise, not to prove them right, but to try and prove them wrong. The theories that survive this process of relentless criticism and attempted refutation are the ones that we provisionally accept as our best current knowledge. This is a process that is fundamentally about the growth of explanatory power. A good scientific theory is not just one that fits the facts. It is one that provides a deep, coherent, and hard-to-vary explanation for why the facts are the way they are. Newton's laws of motion did not just describe the elliptical orbits of the planets. They explained them as a consequence of a single, universal law of gravitation. This is the difference between a description and an explanation. And it is the search for these deep, unifying explanations that is the true engine of scientific progress. This leads to a profound and perhaps counterintuitive idea. Science does not and cannot have an ultimate, unshakable foundation. The search for a source of absolute justification for our knowledge, a bedrock of truth, is a philosophical dead end. There is no such thing. All our knowledge is conjectural, fallible, and open to improvement. This may sound unsettling, like a recipe for radical skepticism, but it is, in fact, the very source of science's strength. It is because our knowledge is not built on a fixed, dogmatic foundation that it is able to grow, to adapt, to evolve. It is like climbing a mountain that has no summit. Each new step takes us higher, gives us a wider and clearer view, but also reveals a new, more distant horizon of what we do not yet know. The rationality of science lies not in its ability to prove its theories to be true, but in its relentless, self-critical process of seeking out and eliminating error, of constantly striving to replace our current good explanations with ever better ones. This evolutionary problem-solving view of science is beautifully illustrated by the Turing principle, a concept that connects the nature of computation with the very comprehensibility of the universe. The Turing principle, in its essence, states that it is possible to build a universal virtual reality generator, a computer that can simulate any physical environment that is allowed by the laws of physics. This has a profound implication. It means that the universe is, in a fundamental sense, knowable. The laws of nature are such that they can be understood, they can be modeled, and they can be simulated by a universal computer, which is itself a physical object within the universe. The human mind, with its capacity for creative conjecture and rational explanation, is, in this sense, a kind of universal explainer. The fact that we are able to create knowledge, to understand the deep and often counterintuitive laws of the cosmos, is not just a lucky biological accident. It is an intrinsic and perhaps even necessary feature of the kind of universe we inhabit. The universe seems to have a built-in capacity for being understood, and we are the vehicles for that understanding. This brings us back to the question of what it means for a theory to be true. In this fallibilist, Popperian view, we can never declare a theory to be definitively, absolutely true. The process of corroboration, where a theory survives numerous and severe attempts to falsify it, gives us a high degree of confidence in it. But it is not the same as proof. No theory is ever immune from the possibility of being superseded by a better one in the future. Newton's laws were considered the bedrock of physics for centuries, but they were eventually shown to be an approximation, a special case of Einstein's more general theory of relativity. And Einstein's theory, in turn, is likely to be superseded by a future theory of quantum gravity. This does not mean that Newton was wrong. It means that his explanation was of limited reach, and has now been subsumed into a deeper, more comprehensive explanation. This ongoing, open-ended process of refinement is the very essence of scientific progress. So, how do we act? How do we make decisions? In a world where we can never have absolute certainty, we act on the basis of our best available explanations. When we build a bridge, we use the principles of modern engineering, not because they are proven to be absolutely true, but because they are the best, most resilient, and most well-tested explanations we have for how to build a structure that will not collapse. The power of science lies not in its ability to provide us with final, dogmatic truths, but in its utility, in its remarkable ability to solve problems, to create new technologies, and to deepen our understanding of the world. It is a process that is driven not by a search for authority, but by a commitment to creativity, to criticism, and to the relentless, and ultimately joyful, pursuit of better and better explanations. And for those of us who look up at the stars and are filled with a sense of wonder, it is this very open-endedness, this promise of endless discovery, this constant striving for a deeper and more beautiful understanding of the cosmos, that makes the scientific journey so profoundly exciting. The ancient thinkers, from Aristotle to the natural philosophers of the Renaissance, often perceived living beings as being fundamentally and qualitatively distinct from the inanimate world. They saw in life a special spark, a vital force, or entelechy, an ability to initiate motion and to act with purpose that set it apart from the passive, mechanical world of non-living matter. But with the rise of modern materialistic science, this view was largely dismantled. Life, in the modern reductionist perspective, is often seen as being nothing more than a complex chemical process, a particularly intricate and self-organizing arrangement of atoms and molecules, governed entirely by the same universal physical laws that direct the motion of the planets and the decay of radioactive elements. And yet, even within this powerful and successful framework, life remains a profound and undeniable enigma. It is a phenomenon of such staggering complexity, such remarkable purposefulness, and such creative power that it seems to demand a special place in our understanding of the cosmos. Life is not just a passive result of the laws of physics. It is an active, knowledge-creating, and world-shaping force, a phenomenon that gives the universe a unique and dynamic character. Unlike the inert matter that makes up the vast majority of the cosmos, which drifts passively according to the laws of motion and thermodynamics, life acts with intention. It adapts, it learns, it evolves. It actively works to counter the relentless slide towards entropy, creating pockets of incredible order and complexity in a universe that is, on the whole, becoming more disordered. To understand life, therefore, is not just a problem for biology, it is a central problem for cosmology. We cannot hope to have a complete picture of the universe without acknowledging and accounting for the strange, wonderful, and perhaps even cosmically significant phenomenon of life. At the very core of what makes life so special is its intimate relationship with knowledge. Every living organism, from the simplest bacterium to the most complex human being, is an embodiment and a creator of knowledge. This knowledge is not just abstract information. It is functional, practical, and time-tested wisdom about how to survive, how to reproduce, and how to navigate the challenges of a particular environment. The most ancient and fundamental repository of this knowledge is the DNA molecule. Within the elegant double helix structure of DNA lies the genetic program of life, an incredibly intricate and densely packed code that stores the accumulated wisdom of billions of years of evolution. It is a blueprint, a recipe, a historical archive, a survival manual, all written in a simple four-letter alphabet. This molecular program is a stunning example of how knowledge can be physically instantiated and propagated through time. Through the twin processes of replication and mutation, life has mastered the art of both preserving its hard-won knowledge and generating the new variations that are necessary for future adaptation. But the creation of knowledge is not limited to the slow generational process of genetic evolution. In more complex organisms, another, much faster, kind of knowledge creation has emerged, the knowledge created and stored in neural systems. The human brain is the most complex and sophisticated knowledge-creating entity we know of in the universe. It is a biological computer of almost unimaginable power, capable of creating abstract models of the world, of generating novel explanations, of creating art, of contemplating its own existence. And the knowledge created by human minds is not just stored in our individual brains, it is propagated and amplified through the medium of culture. The memes, as the biologist Richard Dawkins called them, the ideas, the stories, the technologies, the scientific theories are a new kind of replicator, a new form of knowledge that evolves and spreads through human societies, allowing for a rate of adaptation and change that is orders of magnitude faster than genetic evolution. This dual system of knowledge creation, the genetic and the mimetic, gives life, and particularly intelligent life, a truly extraordinary power. It is the power to not just adapt to the environment, but to actively reshape it. And as we look to the future, the potential scale of this reshaping is almost limitless. Cosmologists and futurists speculate that a sufficiently advanced, intelligent civilization may one day be able to influence the cosmos on a galactic or even a universal scale. They might learn to harness the energy of entire stars, to build vast, self-replicating habitats, to re-engineer planetary systems, or even to influence the very laws of physics in their local corner of the multiverse. These are not just fanciful science fiction notions. They are plausible, long-term extrapolations of the knowledge-creating trajectory that life has been on since its inception. This perspective, which sees life as a fundamental, knowledge-creating, and world-shaping force, has profound implications for our understanding of the universe. It suggests that the long-term fate of the cosmos may not be solely determined by the blind, impersonal forces of physics like gravity and entropy. It may also be shaped, and perhaps even ultimately determined, by the purposeful actions of intelligent, living beings. On the one hand, life might seem to be an insignificant and fleeting phenomenon when compared to the sheer, overwhelming scale of the cosmos. The total mass of all the living organisms on Earth is a tiny, infinitesimal fraction of the mass of a single star. But to judge the significance of life by its mass is to make a category error. The true significance of life lies not in its physical presence, but in its influence, in its unique and remarkable ability to generate knowledge and to use that knowledge to create change. A single, well-formed idea, a scientific theory or a new technology, can have an impact that is vastly out of proportion to its physical substrate. It can change the course of history on a planet, and perhaps, one day, on a much larger scale. In this sense, life may be the most potent and significant phenomenon in the entire universe. It is the universe's own, built-in mechanism for generating complexity, for creating novelty, and for exploring the vast landscape of what is possible. This connects back to the Turing principle, the idea that the universe is fundamentally computable. Life, and particularly the human mind, can be seen as the universe's own homegrown universal computer, a system that is capable of understanding and modeling the very laws that gave rise to it. The fact that the universe has produced a system that can comprehend it is not just a lucky accident. It may be a deep and fundamental feature of its structure. The universe is not just a set of physical laws. It is a system that supports the creation and evolution of knowledge itself. This brings us to a beautiful and powerful vision. Life is not an anomaly in a dead universe. It is the universe's own creative edge. It is the leading wave in the cosmic story of increasing complexity and understanding. And we, as human beings, are at the forefront of this wave. The decisions we make, the knowledge we create, the future we choose to build, these are not just matters of local, terrestrial concern. They are events of potential cosmic significance. The future of life in the universe, the future of knowledge, the future of the cosmos itself, may depend, in some small but real way, on what we do next. This is a vision that is both humbling and inspiring. It is humbling because it reminds us of our deep connection to, and dependence on, the larger cosmic ecosystem. And it is inspiring because it endows our lives, our choices, and our quest for knowledge with a profound, and perhaps even ultimate, meaning. We are not just spectators of the cosmic drama. We are its protagonists, its authors, the agents through whom the universe is writing its own, and as yet unfinished, story. Mathematics is often perceived as a realm of pure, timeless, and abstract truth, a world of perfect forms and unshakable certainties that exists independently of the messy, physical world of our experience. But what if this Platonic vision is an illusion? What if mathematics is not a separate, transcendent reality, but is deeply and inextricably intertwined with the physical world, a product of the very same laws of nature that govern the stars and the atoms? This is a perspective that challenges our most deeply held beliefs about the nature of truth and knowledge, but it is one that is increasingly supported by our understanding of computation, physics, and the workings of the human mind. Take the very concept of a number. It seems like a pure abstraction, but the process by which we manipulate numbers, the process of calculation, is a physical one. It requires a physical system, an abacus, a piece of paper and a pencil, a digital computer, or the neural networks of a human brain to be carried out. And these physical systems are all governed by the laws of physics. The reliability of a mathematical proof is not just a matter of its logical consistency. It is also contingent upon the reliability of the physical processes that are used to check it. If the computer that runs a proof is subject to random quantum fluctuations that flip its bits, or if the brain that conceives of it is subject to the frailties of memory and attention, then the certainty of the proof is no longer absolute. It becomes a matter of physical probability. This idea is deepened by the work of the mathematician Kurt Gödel. His famous incompleteness theorems, published in 1931, delivered a devastating blow to the dream of a complete and provably consistent foundation for all of mathematics. A dream championed by the great mathematician David Hilbert. Gödel showed that in any sufficiently complex and consistent mathematical system, there will always be true statements that cannot be proven within that system. To prove them, you have to step outside the system and introduce new axioms. But this new, larger system will have its own, new unprovable truths, and so on, ad infinitum. This means that mathematics is not a closed, static, and complete system of eternal truths. It is an open-ended, creative, and constantly evolving enterprise. It requires the constant invention of new concepts, new axioms, new ways of thinking, and this process of invention is not a purely logical one. It is a creative, psychological, and ultimately physical process, carried out by physical beings with physical brains. The history of mathematics is a testament to this creative, evolutionary process. The axioms of Euclidean geometry, which were considered self-evident truths for over 2 millennia, were eventually challenged, leading to the development of the new non-Euclidean geometries of Riemann and Lobachevsky. And these new, abstract geometries turned out to be not just mathematical curiosities, but the essential language needed to describe the curved spacetime of Einstein's general theory of relativity. The map and the territory, the abstract and the physical, are in a constant dynamic dialogue, each shaping and reshaping the other. This deep entanglement of mathematics and physics suggests that the Platonic view of mathematics as a separate, transcendent realm may be a beautiful, but ultimately misleading metaphor. Mathematical entities, the numbers, the shapes, the equations, do not exist in some heavenly, non-physical world. They exist, in a very real sense, in the physical world as patterns of information, as states of computational systems, as emergent properties of the laws of nature. This is a perspective that has been championed by the physicist David Deutsch, who argues that mathematics is a branch of physics. The truths of mathematics are not abstract, a priori truths. They are truths about the computational capacities of the physical world. The reason that 2 + 2 = 4 is not because of some abstract, Platonic law, but because the laws of physics that govern the behavior of a universal computer guarantee that any physical system that correctly performs the computation 2 + 2 will arrive at the physical state that we label 4. In this view, a mathematical proof is not an abstract, logical argument. It is a description of a physical process, a computation. And the validity of the proof depends on the physical possibility of performing that computation. This is a profound and radical shift in our understanding of mathematics. It takes it down from its Platonic pedestal and grounds it in the messy, contingent, and beautiful reality of the physical world. it also helps to explain the unreasonable effectiveness of mathematics in the natural sciences. A puzzle famously articulated by the physicist Eugene Wigner. The reason mathematics is so good at describing the physical world is not a miracle. It is because mathematics is the study of the computational structure of the physical world. They are two sides of the same, deep coin. This perspective does not diminish the beauty or the power of mathematics. On the contrary, it enriches it. It shows us that mathematics is not a sterile, static, and inhuman system of logic, but a living, breathing, and deeply human endeavor, a creative exploration of the very fabric of reality. The illusion of mathematical certainty, the idea that it provides an unshakable foundation for our knowledge, is a powerful and persistent one. But it is an illusion that we may need to let go of in order to arrive at a deeper and more authentic understanding of the world. What we are left with is not a failure, but a new and more profound appreciation for mathematics as a process of discovery, of explanation, of creativity, a process that is intimately and inextricably linked to our own physical and embodied existence as knowledge-creating beings in a knowable universe. The nature of time is perhaps the most profound, perplexing, and personal of all scientific and philosophical mysteries. We feel its passage in our very bones. We experience our lives as a continuous, flowing narrative, a journey from a remembered past through a fleeting present to an anticipated future. This experience of a flowing, moving now is so fundamental, so deeply ingrained in our consciousness, that it seems to be an undeniable feature of reality itself. And yet, when we turn to our best and most fundamental physical theories, this familiar, flowing river of time seems to evaporate into a strange and static landscape. This is the great paradox of time, the stark and seemingly irreconcilable conflict between the time of our subjective experience and the time of our physical theories. The common sense, intuitive view of time is that of a universal, cosmic river, carrying everything along in its current. The present moment is a special, privileged point in this flow, a moving frontier that separates the fixed, unchangeable past from the open, potential future. This is a powerful and deeply rooted metaphor, but it is one that is not supported by modern physics. Albert Einstein's theory of relativity, both special and general, delivered the first major blow to this classical picture. Einstein showed that time is not absolute, but is relative to the observer. Two observers moving at different speeds will experience time at different rates. For an astronaut traveling near the speed of light, time will slow down relative to an observer on Earth. This time dilation is not a psychological illusion. It is a real physical effect, confirmed by countless experiments. This means that there is no single, universal now. My now is not the same as the now of an observer in a distant galaxy. The concept of a simultaneous, universal present moment is a casualty of relativity. Instead, Einstein's theory gives us a picture of a four-dimensional spacetime, a unified fabric in which space and time are inextricably interwoven. In this picture, all of time past, present, and future is laid out, once and for all, in a single, static, four-dimensional geometry. This is the block universe view of time. In this view, there is no flow, no movement, no becoming. The past is not gone, and the future is not unreal. They are all just different regions of the space-time block. The dinosaurs are not extinct. They are just located in a different part of space-time. Our own future already exists, in the same way that a distant city already exists. We are just not there yet. The feeling of the flow of time, in this view, is a subjective illusion of our own consciousness, a trick of the mind that creates the impression of movement through this static landscape. But this is a deeply unsatisfying explanation for many. How can a universe in which nothing ever truly changes give rise to an experience that is so defined by change? This brings us to the quantum world, which adds another layer of strangeness and complexity to the mystery of time. Quantum mechanics, with its inherent indeterminacy and its focus on measurement, seems to reintroduce a distinction between the past and the future. A quantum system exists as a superposition of possibilities before a measurement, and as a single, definite outcome after a measurement. The act of measurement seems to be a moment of irreversible change, a point where the open potential of the future collapses into the fixed fact of the past. This has led some to suggest that the arrow of time may be rooted in this fundamental quantum process of wave function collapse. But the many worlds interpretation of quantum mechanics offers a different perspective, one that is remarkably consistent with the block universe of relativity. In the many worlds view, there is no collapse. The universe is a constantly branching tree of parallel realities, with each branch representing a different possible outcome of a quantum event. In this picture, all possible pasts and all possible futures exist simultaneously in a vast quantum multiverse. Our experience of a single linear timeline is just our journey through one particular branch of this infinite branching reality. The flow of time is the process of our consciousness moving from one snapshot of a particular branch to the next. The profound disconnect between the static, geometric time of physics and the dynamic, flowing time of our experience remains one of the greatest unsolved problems in all of science. It is a problem that touches on the deepest questions about the nature of reality, of causality, of free will, and of consciousness itself. If the future already exists, as the block universe model suggests, then what does it mean for us to make a choice? Is our feeling of free will just another illusion, our lives just the playing out of a pre-written script? The compatibility of free will with a deterministic or block universe is a long-standing philosophical debate. One possible reconciliation is to see free will not as a violation of the laws of physics, but as an emergent property of complex computational systems like our brains. We are free in the sense that our actions are not determined by external forces, but by our own internal, complex processes of deliberation and choice, even if those processes themselves are ultimately governed by deterministic physical laws. But the quantum multiverse offers an even more radical, and perhaps more satisfying, perspective. In the many worlds view, every choice we make may be real. When we are faced with a decision, the universe itself may branch, with different versions of ourselves living out the consequences of each possible choice in a different parallel reality. In this sense, we have a profound kind of free will. We are not choosing one path and eliminating the others. We are actualizing all possible paths, and our consciousness simply experiences the journey down one particular branch. This is a breathtaking and deeply humbling vision of reality. But what about time travel? The idea of moving through time, both to the future and to the past, is a staple of science fiction, and it is a concept that is not entirely ruled out by our current understanding of physics. Future-directed time travel is, in a sense, a proven fact. The time dilation of special relativity means that an astronaut traveling at near-light speeds is effectively traveling into the future of the Earth. Similarly, technologies that could slow down our biological processes, like suspended animation, would be a form of one-way travel to the future. Past-directed time travel, however, is a far more problematic and speculative concept. General relativity does allow for certain exotic solutions to its equations that contain closed, time-like curves, loops in spacetime, that would allow an object to travel back to its own past. These could, in theory, be created by certain configurations of matter and energy, like a spinning, cylindrical universe or a traversable wormhole. But these solutions often require the existence of exotic matter with negative energy density, something that may not be physically possible. And even if a time machine could be built, it would immediately run into the famous paradoxes of causality, like the grandfather paradox. If you go back in time and prevent your own grandfather from meeting your grandmother, you would never be born, and therefore you could not have gone back in time to do so. This seems to be a logical contradiction. The many worlds interpretation of quantum mechanics offers a neat, if unsettling, solution to these paradoxes. If you travel back in time, you do not travel back into the past of your own universe. You travel to a different, parallel branch of the multiverse. You can change the past in that universe, but it will have no effect on the history of the universe you came from. The grandfather paradox is resolved, but at the cost of being forever stranded in an alternate reality. The mystery of time is a deep and multifaceted one. It is a puzzle that is not likely to be solved by physics alone. It will require a new, unified understanding that can bridge the gap between the objective, physical world and the subjective, conscious world, between the static landscape of space-time and the dynamic, flowing river of our own, lived experience. And as we continue to explore the universe, to push the boundaries of our knowledge, we are not just learning about the nature of the cosmos, we are also learning about the deep, strange, and beautiful nature of time itself. The quest to understand the fabric of reality, in all its richness and complexity, is not a journey that can be undertaken by any single discipline in isolation. It is an endeavor that requires a deep and fruitful collaboration between the different, and sometimes seemingly disparate, ways of knowing that humanity has developed. To truly grasp the universe, we need a unified, explanatory framework that can weave together the insights of quantum physics, of epistemology, of computation, and of evolution. These are the four fundamental strands of reality, and it is only by understanding how they are intertwined that we can hope to arrive at a truly comprehensive picture of the world. The first of these strands is quantum physics. It is the pillar of our modern understanding of the physical world, the theory that explains the fundamental mechanisms that govern the behavior of matter and energy. Quantum mechanics, and particularly its many worlds interpretation, reveals a universe that is far vaster, more complex, and more deeply interconnected than our classical intuition would ever lead us to believe. It shows us a reality that is not a single, definite state, but a branching, probabilistic multiverse, a symphony of intertwined possibilities. But physics alone, for all its power, cannot answer certain deeper questions. It can tell us how the universe works, but it cannot, by itself, tell us how we know how the universe works. This is the domain of epistemology, the second crucial strand. Epistemology is the theory of knowledge. It explains how our scientific theories are created, how they are tested, and how they evolve over time. It teaches us that knowledge is not a static, finished product, but a dynamic, open-ended process of conjecture, criticism, and refinement. Without a robust epistemology, we would be lost in a sea of competing ideas, with no rational way to distinguish between a good explanation and a bad one. The third thread in this grand tapestry is the theory of computation. Computation is not just about the processing of numbers in a digital computer. It is a deep and fundamental concept that describes how information is represented, transformed, and manipulated in any physical system. The laws of physics themselves can be seen as a form of computation, a set of rules that governs how the state of the universe evolves from one moment to the next. The Turing principle, which states that a universal computer can simulate any physical process, suggests a deep and profound link between the laws of physics and the laws of computation. It suggests that the universe is, in a fundamental sense, an information processing system. Completing this quartet is the theory of evolution. Evolution, in its broadest sense, is not just about the biology of genes and organisms. It is a universal principle that explains the emergence of complexity and adaptation in any system that has a mechanism for replication, variation, and selection. It explains how, from simple beginnings, intricate and purposeful-seeming design can emerge without a designer. We see this principle at work in the evolution of life, in the evolution of our scientific theories, and perhaps even, as some have speculated, in the evolution of universes within a multiverse. These four strands, quantum physics, epistemology, computation, and evolution, are the fundamental pillars of our modern understanding of reality. But they cannot be viewed in isolation. To do so is to see only a partial, and often distorted, picture. A reductionist approach that tries to explain everything in terms of physics alone will inevitably fail, because it cannot account for the emergent and equally fundamental realities of knowledge, of computation, and of life. These are not just complex applications of physics. They are fundamental principles in their own right, with their own explanatory power. A true theory of everything will not be a theory of physics alone. It will be a unified explanatory framework that shows how these four strands are interwoven, how they support and illuminate each other, how they come together to form a single, coherent, and beautiful fabric of reality. The quest for this unified, four-stranded understanding of reality is hampered by a number of deep and as yet unresolved explanatory gaps. These are not just areas where we lack data. They are areas where our current fundamental theories seem to be in conflict, or where they fail to provide a satisfying explanation for a key aspect of reality. The conflict between quantum mechanics and general relativity. The problem of quantum gravity is perhaps the most famous of these, but there are others that are just as profound. There is a deep explanatory gap between the theory of computation and the rest of physics. We know that information is physical, that it must be embodied in a physical system. But how does the abstract mathematical world of computation emerge from the underlying physical laws? What is the relationship between the bits of information and the its of physical reality? This is a question that touches on the deepest mysteries of both physics and information theory. Similarly, there is a gap between the theory of evolution and the other strands. Evolution by natural selection is a powerful explanation for the adaptation of life, but it does not, by itself, explain the origin of life, the transition from non-living chemistry to the first self-replicating organism, nor does it fully explain the emergence of open-ended knowledge creation, the kind of universal explanatory power that seems to be unique to the human mind. Why has evolution on this planet produced a system that is capable of understanding the laws of the cosmos? This seems to be a phenomenon that requires a deeper, more fundamental explanation. And even within quantum mechanics itself, the most successful of our fundamental theories, there remain deep conceptual puzzles. The measurement problem, the nature of entanglement, the role of the observer. These are all areas where our current understanding is incomplete, where the theory seems to be pointing towards a deeper and stranger reality that we have not yet fully grasped. These explanatory gaps are not a sign of failure. They are the growing pains of a rapidly advancing science. They are the frontiers of our knowledge, the places where the next great revolutions in our understanding are likely to occur. But they are also a breeding ground for a philosophical stance that can be a major impediment to progress instrumentalism. Instrumentalism is the idea that scientific theories are not, and should not be, attempts to explain reality. They are merely instruments, tools for making predictions about the outcomes of experiments. In this view, a theory is judged not by its explanatory power, but solely by its predictive accuracy. Shut up and calculate is the famous and often misattributed motto of the instrumentalist. This is a tempting, and in some practical contexts, useful stance. But as a general philosophy of science, it is a dead end. It abandons the very thing that makes science so powerful and so exciting, its ability to provide us with a deeper understanding of the world. Prediction is a valuable and necessary part of science, but it is not its goal. The goal is explanation. A theory that can accurately predict the positions of the planets, but offers no explanation for why they move in that way, like the Ptolemaic system, is ultimately a scientific failure. A theory that not only predicts, but also explains, like Newton's or Einstein's, is a profound and lasting human achievement. The quest for a unified, four-stranded understanding of reality is a quest for explanation. It is the search for a single, coherent story that can make sense of the universe in all its multifaceted glory. It is a quest that requires us to be both bold in our conjectures and humble in the face of our own profound ignorance, and it is a quest that is driven by a deep and uniquely human desire not just to observe the world, but to understand it. A truly unified understanding of reality, one that seamlessly weaves together the four strands of quantum physics: epistemology, computation, and evolution, would have profound and transformative implications for our future. It would not just be an intellectual achievement, it would be a practical one, with the potential to revolutionize our technology, our society, and our very sense of what it means to be human. Consider, for example, the future of artificial intelligence. Our current approaches to AI, while impressive in their own right, are largely based on a form of sophisticated instrumentalism. Machine learning algorithms are incredibly good at finding patterns in data and making predictions, but they do not, for the most part, create genuine, explanatory knowledge, a true artificial general intelligence. An AI with the same kind of creative, open-ended, and explanatory power as a human mind will likely require a deeper, more unified understanding of the nature of knowledge itself. It will require a theory of artificial epistemology, a set of principles for how a computational system can generate and test new explanatory ideas. The development of such a theory would be a direct consequence of a deeper integration of the four strands. It would require us to understand how the process of knowledge creation, as described by epistemology, can be implemented in a computational system, as described by the theory of computation, that is itself grounded in the laws of quantum physics and has been shaped by a process of evolution. The creation of a true AGI would be a world-changing event, a moment when humanity transcends its own biological limitations and creates a new, and potentially far more powerful form of knowledge-creating intelligence. Or consider the future of medicine. Our current reductionist approach to biology has been incredibly successful, but it has its limits. A deeper, more holistic understanding of life as a phenomenon that is not just about physics and chemistry, but also about information, computation, and evolution, could lead to a new and far more powerful kind of medicine. Imagine therapies that are based not just on manipulating the molecular hardware of our cells, but on reprogramming their informational software. Imagine a medicine that understands and can work with the complex, adaptive, and evolutionary nature of disease. This would be a medicine that is not just about treating symptoms, but about restoring the deep, informational and computational integrity of the living system. This, too, would be a direct consequence of a more unified, four-stranded understanding of reality. But perhaps the most profound implication of this unified vision is its potential to reshape our own human worldview. The current fragmented state of our knowledge often leads to a sense of alienation and meaninglessness. The physical universe of science can seem cold, impersonal, and purposeless. The world of human values, of meaning, of consciousness, can seem to be a separate and ultimately illusory realm. A unified, four-stranded explanation of reality would heal this wound. It would show us how the physical, the epistemic, the computational, and the biological are not separate domains, but are different and equally fundamental aspects of a single, unified, and deeply meaningful reality. It would show us that we are not strangers in a dead universe, but are an integral and significant part of a cosmos that is, in its very nature, creative, knowledgeable, and evolving. It would provide a new and deeply rational foundation for a sense of wonder, of purpose, and of our own profound connection to the grand cosmic story of existence. The quest for a unified theory of everything is not just a quest for a final equation. It is a quest for a new way of seeing, a new way of being, a new and more complete understanding of who we are and why we are here. It is the most ambitious and the most important journey that humanity has ever undertaken,